In this video, we're going to talk about the divergence and curl in R3. So in the last video, we mentioned divergence and curl, and this was in R2. And these were part of the exploration that we looked into for Green's theorem. So for a vector field, let's just define that first. Our vector field is going to be f, such that the x component is f of xy, and the y component is g of xy. Now the two-dimensional divergence, we'll just say 2D divergence of our vector field f was, if you remember, the integrand of Green's theorem if you were considering the flux form of the theorem. So this is just equal to the partial derivative of f with respect to x plus the partial derivative of g with respect to y. Now the divergence, what that tells us is that it's actually a measure of the expansion and contraction of a vector field at each point. So of our vector field f at each point. So the divergence, we'll just say div, if the divergence of f, if it's 0, we mentioned this prior in the video before, if the divergence is 0 throughout our region, and remember the region has to be simply connected, so if the divergence is 0 throughout this region, what that means is that our vector field f is considered to be source free. Okay, and what that implies is that the outward flux across the boundary of our region, so outward flux across the boundary of our region, we'll call it R, across boundary of R, is also 0. Okay, so we have now this idea, and we're just going to extend it into R3. So first of all, let me remind you of something when learned about gradients. So the gradient of we'll just go with the del operator. So this symbol here, the del operator, represented the partial derivative. So this is going to be the partial derivative with respect to x, with respect to y, and with respect to z. Okay. Now our divergence is going to use this del operator in the definition. So we assume that our vector field, so we'll go ahead and just do this as a definition. We're going to define divergence in R3 now. So we assume that our vector field f is f, g, h. We assume that this is differentiable on our region, and this time our region is in R3. And so the divergence of f, we're now going to abbreviate it. It's written as div, so divergence of f is equal to the dot product of this del operator, del, dotted with our vector field f. And this is going to be equal to the partial derivative of f with respect to x plus the partial derivative of y with respect, g with respect to y plus the partial derivative of z with respect, I'm switching them, the partial derivative of h with respect to z. There we go. F with respect to x, g with respect to y, h with respect to z. Okay. So this is our definition here. Now, just kind of carrying over on this idea of the divergence being 0, if the divergence, which is now defined as this dot product of del dotted with f, if this is 0, we already know what that means. This means that f is source free once again on R, on our region. And also, so if it's not 0, let's mention what happens there. So if this divergence is, let's say, positive, then what this means is f acts as a source in R. Okay, source in R. In our region. It could be R. I'm just calling it R for now. And also, if the divergence is negative, well then that means that F acts as a sink in our region, in R. As a sink. And this just depends on your orientation in R, whether you're going to call it a sink or a source. Okay, so now let's identify the divergence for a special type of vector field, the radial vector field, and then we'll go ahead and look at an example. Okay, so the divergence of a radial vector field, we have the following. So divergence, let's just abbreviate some stuff, of radial vector field. This is going to be for, well, first of all, let's define the vector field. F, if you recall, a radial vector field is can be defined as R divided by the magnitude of R and raised to the power P. P is any real number, and this is going to be equal to the vector defined as x, y, z over the magnitude here. So x squared plus y squared plus z squared raised to the p over 2 power. Okay, so if this is our radial vector field, then the divergence of this, so divergence of F in this case, is going to still be equal to this dot product of del dot with dotted with F. And if you work this out, you can do this the long way, but if you work this out, it ends up being really nice. It's just 3 minus p over the magnitude of R to the p power. Okay, so you don't technically have to memorize this formula here, but you can work it out based on the previous definition down here. But this is definitely a time saver if you do want to use this version of the formula, if your vector field is a radial vector field. Okay, so let's consider an example and calculate or evaluate the divergence. So our example, we are going to use this vector field, x, y, z. This is all going to be divided by 4 plus 6x squared plus y squared, and we're calculating the divergence. So what we want to know is what's the divergence of F. Okay, so based on the previous definition, I just erased it, but we need the partial derivatives. Okay, so we need the partial derivative of F with respect to x. Okay, so if you want, you can rewrite this to make it a little bit more clear, but each of these components, x, y, z, they all are going to have this denominator of, right here, 4 plus 6x squared plus y squared. So when we take this partial derivative, we're actually going to use the quotient rule. So this is going to be the derivative of the top, the numerator, which is 1, because we're differentiating with respect to x, times the derivative of the bottom, the denominator. I'm sorry, times the bottom, not the derivative, minus the top, the numerator, now times the derivative of the bottom. Now remember, we're differentiating with respect to x, so the only thing that's not a constant is this middle term here. So differentiating this, we get 12x, and all divided by our denominator squared. And we're going to do this for all 3 components here. Okay, so the partial derivative of y with respect to, I'm sorry, I keep saying yg with respect to y. Same idea, derivative of the top times the bottom minus the top, which is y, times the derivative of the bottom. Now the bottom this time, we're considering only y to be a variable that we're differentiating, so this is going to turn into y all over our denominator squared. I forgot the square the last time. There we go. Squared. And one more time, the partial derivative this time of h with respect to z. And the same idea, we have derivative of the top, which is 1, times the bottom. Now when we subtract the derivative of the bottom times the top, notice there's no z's down here, so when we take the derivative, this is just a constant, and the derivative is 0. All over our denominator here, squared. Okay, and then using the formula for our divergence, we're just going to take the sum of all of these. Okay, and that's going to give us our result. So we'll go ahead and notice we have the same denominator for all three terms. So we're going to keep that denominator. So the divergence of f is going to be over our common denominator, 4 plus 6x squared plus y squared, quantity squared. And let's just go ahead and do the algebra over here real quick. So we end up with 12x squared when we combine this these two factors, 2y squared when we combine these factors, and let's just go ahead and combine like terms. So notice each of these factors at the beginning of each numerator is times 1, so we'll combine our constants, 4, there's no other constants, plus 4 plus 4, so we end up with 12. Okay, then let's go to the x squareds. 6x squared plus 6x squared plus 6x squared, we are at 18. Take away this 12, so we have plus 6x squared. And then y squared plus y squared plus y squared, take away 2y squared, gives us 1y squared. And this is our divergence of our vector field here defined, our vector field f. Alright, so we are also going to look at, real quick, let me give you a rule for the product of a divergence. So product rule for divergence, let's go ahead and erase this example. Okay, so product rule for divergence, and I'll just again abbreviate it, divergence. We have our del operator dotted with u of f, or times f, where u is just a scalar valued function. So it's differentiable, it's the scalar valued function, it's differentiable on the region, whatever our region is. F is our vector field, which is also differentiable on our region. So this is equal to del, or the gradient of now of u dotted with f plus u times del dotted with f. Okay, so this is our product rule for divergence. Alright, now we want to consider the curl in R3. So we're ready for the curl in R3. Okay, so let's recall. From before, we mentioned curl in the previous video about Green's theorem. The two-dimensional curl, or 2D curl of our vector field f. So we'll just continue to define f as before for 2D. So our two-dimensional curl of f was the integrand from Green's theorem, the circulation form. So the partial derivative of g with respect to x minus the partial derivative of f with respect to y. And the curl, what this does is it measures the rotation of our vector field at a point. So it measures the rotation of our vector field f at a point. Now remember, if the curl was equal to 0, and this is throughout our simply connected region, so if the curl is 0, then that meant that f was irrotational, or because of the simply connected region, it was conservative. So f is conservative. And what that means, or implies, is that the circulation on the boundary of our region, we'll call it R, circulation on the boundary, of our region, we'll call it R, is also 0. Okay? So now let's define the curl in 3 dimensions. So let's go ahead and go up here. Alright, so we have, we're basically going to extend this into 3 dimensions here. So we have now that, again, f is defined as f, little g, little h. So the curl of f, which is denoted just curl f, is going to be the cross product. So remember, the divergence was the dot product. Curl is now the cross product of our del operator with f. And this is going to equal the partial derivative of h with respect to y. This one's a little bit longer. So minus the partial derivative of g with respect to z. This is our I component. Okay. I'll go ahead and just write it out vertically here. Plus the partial derivative of f with respect to z minus the partial derivative of h with respect to x. This is our j component. And lastly, the partial derivative of g with respect to x minus the partial derivative of f with respect to y. And that's our k component. Okay, so this is our definition for curl in R3. So if the curl, just what we mentioned about a moment ago, if the curl of f is 0, so curl of f is, and we now know the cross product, if this is 0, then this means that f is irrotational or conservative. So we'll say irrotational. Alright, now let's go ahead and do an example, and then I'll give you some important theorems here at the end. So example, let's define f as 2x squared minus 5y squared, 3xy, and 4z. Now we want to compute the curl. So the curl of f, it's going to be this cross product here. And we could do this out the long way, but we have this nice formula or definition above, so we're going to go ahead and do that. So let's go jump right into this form. I'm going to set up the form. We have subtraction, and then we are going to be adding up each of these components. So this is the I component plus this difference for our j component, and plus this difference for the k component. Okay, so I want, first of all, I want the partial derivative of h with respect to y. So let me identify really quick for you what's f, g, and h. So right here, this is going to be f, little f, this is g, and this is h. Okay, let's make sure you can see this squared value here. Okay. So we have the partial derivative of h with respect to y. So h with respect to y, there is no y, so this is 0. Okay. Let's go ahead and use blue just to make it stand out a little bit more. So the partial derivative of h with respect to y, there is no y. This is 0. Minus the partial derivative of g with respect to z, there is no z, so that's 0. Now we move on to the second term, second component. Partial derivative of f right here with respect to z, there is no z, so this is also 0. Okay, minus the partial derivative of h right over here with respect to x, no x's, this is 0. Hopefully this last component here, the k component, is interesting. Hopefully there's not all zeros. Partial derivative of g with respect to x, so g, there's an x in there, so differentiate with respect to that, we get 3y, and minus the partial derivative of f with respect to y, we're going to say that's negative 10y. So negative 10y. Okay, and if we put this all together, 0 for the I component, 0 for the j component, and we end up with positive 13yk. Okay, so this is our curl of f. Alright, the last thing to talk about is just to give you a couple of interesting theorems, useful theorems, and then talk about a general rotation vector field, okay, that could be used to find constant angular speed. So first, just looking at divergence and curl together, there's a theorem that states that if our curl is of a conservative vector field, so this theorem is exploring the curl of a conservative vector field, Now, if you remember, if a vector field is considered conservative, then it can be written as the gradient of a potential function. So for our vector field f, so we have some vector field f, because it's conservative, we know that that's equal to the gradient of a potential function phi, and we just assume that this potential function has continuous second partial derivatives on whatever our region is. So now this theorem states that the curl, so the cross product here of our del operator with f, well, if we just replace f, this is the del operator cross with the gradient of phi, this is going to actually be 0. Okay, so this is our theorem of interest. Now another theorem, this one talks about the divergence and the curl. This is the divergence of the curl. So if you take the divergence of the curl, what we end up with is the divergence of the curl. So we're going to say, so the divergence is the dot product. So we're going to dot the del operator with the curl, which is the cross product. This is going to be equal to 0. Okay, so two theorems that may prove to be useful. Now, the last thing to look at is just a definition of a, like I mentioned a moment ago, general rotation vector field. So the general rotation vector field is defined as the following. So general rotation vector field is F, where F is the cross product of A with R. Now A is just a constant vector, so we'll call it A1, A2, A3. And R is just X, Y, Z. Cross, so this is cross product right there. X, Y, Z. So I know my cross sign and my X's look similar. Cross product right there. X, Y, Z. Okay, and this is going to be considered the axis of rotation, this constant vector. Axis of rotation. Okay, so this cross product defines what we call a general rotation vector field. Now there's some interesting consequences of this. The magnitude of the cross product of the del operator with F, or the curl. So the magnitude of the curl here is just going to be twice A, whatever A is, absolute value of A. And then the divergence, the del operator dotted with F, is going to be 0. Okay. Now the last thing to mention from this definition of a general rotation vector field is that if F is a velocity field, so is a velocity field, then the constant angular speed is given with the following formula. So the constant, we're going to denote it with omega, constant angular speed, omega, so the constant angular speed of the field is omega, which is the magnitude of A, which is 1/2 of the cross product, or the curl. Okay, so this is the constant angular speed of the field if your field is a velocity field. Okay.